Thank you, Sophia. Good morning, everyone. Thank you for joining our seminar today on the power analysis. We've got a lot to cover today, a lot of interesting subjects, a little bit about Yokogawa and the corporate history. The company was founded in 1915 based on electrical meters, the analog meters, and that were originally sold in Japan. The North American operation began in 1957. Today's worldwide sales are over $4 billion, and we have about 84 different companies worldwide, and a lot of different products and different applications and industries that we serve. There's over 19,000 employees worldwide, operating in about 33 countries. So a little bit about Yokogawa. Today, what we're going to do is talk about power measurements. We're going to start with a review of some of the basics. We'll get into the power measurements using a precision power analyzer, power meter, as well as looking at some of the applications where we can use a power analysis digital oscilloscope. We're going to look at single-phase power measurements, get into current sensors, then look at the three-phase power measurements, look at what we call the 2 and 3 wattmeter method. And then we'll look at some practical applications with the power meters and digital scopes. We're going to look at some important things like Energy Star, standby power, low power measurements, the efficiency and loss measurements on devices, a little bit on power supply analysis with the power digital scope. Then, part 2, we're going to get into power factor measurements. What's displacement power factor? What's true power factor? And again, look at some power factor measurements in single and three-phase circuits and some applications for you. So with that, we'll get started with our first part in basic power measurement. First, let's review some basics. I always like to start out with Ohm's Law. This is the foundation, the fundamentals of everything that we're talking about. And today we're going to be talking about the power part of it, or watts. Basic watt measurement is, a DC circuit, volts times amps, or your I squared R, E squared over R. So again, even though we're going to be talking about some AC and we get into a lot of different types of measurements, this is still the foundation of how we're calculating and doing the power measurement. Some relationships I'd like to go over with you first, and that's the average and mean, you might call it average or half cycle average or mean value compared to the RMS and peak-to-peak values on our waveforms. If we know the RMS value, we know the peak is square root of 2, 1.414. So if we look at the waveform, say on our 120 volt AC line, residential line, we read 120 volts RMS. The peak on that, if we look at it with a waveform analyzer, is going to be the square root of 2. On that sine wave, about 170 volts. Now, if we know the RMS and we want to know what that average is, a half-cycle average, that's a factor of 0.9. And then vice versa, if we know the average, or that half-cycle average, the mean value, we also call this, and we want to get the RMS value, that's a multiplier of 1.11. This comes about when we used to have the analog measuring instruments that were a moving coil, average responding voltmeters, and as an example, and we wanted to scale those to RMS, they had a scale multiplier of 1.11. Well, this is still used in some of our applications even today, and we'll show you some of those a little bit later. Here's some waveform examples of what I was talking about. If we had 120 volt RMS waveform, here's my sine wave, and the top cursor is set at 120 volts. And if we look at the half-cycle average, the mean value, okay, this is 108 volts. And then we look at our measurement function of U mean, which is actually scaled to RMS. it has that 1.11 multiplier on it, you'll see that, okay, it's basically 120 volts. And that's the second cursor right here, which is the 108. So there's a graphical picture of what we're talking about. And again, we will be using those a little bit later. So let's get in now to our electrical power measurement. First of all, what's a watt? Well, it's a unit of power which is equal to 1 joule of energy per second. So in a DC source, our wattage, very simply, is the volts times the amps. The measured voltage times the measured current. Now with an AC circuit, don't forget it's the volts times the amps times the power factor. And we're going to be talking about power factor a little bit later, but AC, we do have to keep that power factor component as a part of our measurements. So AC power measurement, what we call active power, watts, then could be calculated as the RMS voltage times the RMS current times the power factor. And this is sometimes referred to as true power or real power, several different names, but this is a RMS true power measurement. Then the apparent power is what we call volt amps, or the unit of S now in our international symbols. It's S for volt amps, which is just the RMS voltage times the RMS current, volts times amps. So there is a difference between the apparent power, which is the volt amps, and the true power, which is watts, which has the power factor component as part of its measurement. In most of our digital power analyzers today, they're entirely electronic. They use digitizing techniques to convert the analog signals to a digital form. And we use internally digital signal processing to do all the calculations. Now, in a digital scope for true power measurements, there's special firmware in the scope to make these true calculations. So we're not multiplying just one channel times another. The digitizing instruments, we say, are somewhat restricted because it is sampled data. Okay, we are digitizing the waveform, and so it is a sampled data. Most of our power analyzers and the power scopes that we have today on the market, we do have a FFT algorithm that's used for additional analysis of the waveform, look at the harmonic analysis and things like that. We do have another seminar totally based on harmonic analysis with the power analyzers and scopes. Now, in the Yokogawa digital power analyzers, the way we calculate the power is power is average. It's average over time, at least one complete cycle. So we take the instantaneous voltage, digitized value, times an instantaneous current, which is a digitized point, and we multiply these instantaneous values together. We accumulate them over some time period, and then we integrate that value and multiply by 1 over T to get the true power. So this is a true power measurement, regardless of what type of waveform you have, whether it be a sine wave or any type of distorted waveform. So since we're digitizing that waveform, taking those instantaneous values, multiplying together, and then integrating over time, we get a true power measurement. So here's our equations again. Power is the instantaneous voltage times the instantaneous current accumulated and integrated over a time period, just like the RMS values, okay, where we look at just the voltage, what's the instantaneous value of the voltage digitized, and RMS is the root mean squared, so we're taking the square root of that to get the RMS value in the same way with the current. So we do, with these methods, get a true power measurement, and we get a true RMS measurement on any type of waveform. These include all the harmonic content up to the bandwidth of the instrument. Let's compare a power analyzer with a digital storage scope. A lot of people like to use scopes. We're comfortable with those. But let's just look at some of these comparisons. Basically, first thing, bandwidth. Our power analyzers right now, typically from DC up to about 2 megahertz for power. We have scopes that are DC to 500 megahertz and higher. Typically right now we look at power with a scope from about DC to 50 megahertz. And that's really a limitation of the probes that are available to do these accurate calculations for voltage and current. So that's still a limitation of the technology with good current probes up to around 50 megahertz. Accuracy of the power analyzers, anywhere from 0.1 to 0.02%. It is a calibrated measurement system traceable back to international national standards. If you look at the accuracy on the scope, typically it's specified as a DC accuracy, and typical accuracy is about 1.5% at the input terminals. If you're going to measure power, you have to include the probes, voltage and current probes. I say typically around maybe 3.5%, but you have to be careful with that. But it gives you an approximation. With the power analyzers, we can have direct connection of very high voltages and high currents. With the DSO, we do have to use currents. This is current probes and voltage probes. This can be an advantage in that we do have real small current probes for board level work, small current, small level, and that's really where a DSO can help us quite a bit when you're doing your component level and board level work. You're not looking for absolute accuracy, you're looking for a relative measurement, and being able to probe those small places with the probes from a scope is a big advantage right there. Well, let's make a power measurement. We've got some type of a load. Here's a single phase. It's a 2-wire. We've got a load. We've got 2 wires coming out of it. It's a single wattmeter method. We're going to put the wattmeter in series from our source to our load. And we're going to measure the current in series in the line, and we're going to look at the voltage from line to line. And you'll see I do put polarities on there. These are instantaneous polarities. The wattmeter, the power analyzer, on the input terminals will have these polarities. So it's important that we follow the polarities mainly for phase. So we're looking at 2 variables of voltage and current, and we do have to have the right phase relation to make the proper calculation. So in a single phase, 2-wire system, the voltage and the current detected by the meter are the voltage and current applied directly to the load. And this indicates the power that's being dissipated by the load. Now this power meter could be an analog wattmeter, could be a digital power meter, could be the scope. It's the same idea. Well, here's some display. This is right off the display of one of our power analyzers. And we can set this up. So we're looking at the RMS voltage. I had 120 volts. I had about 1 amp and about 96 watts. I had a power factor of 0.7998. Here's the VA, the volt amp measurement S, 120.06. If we take this 120.06 times the power factor, if you got your calculator, you can check that. We should come out with 96 watts. This is the frequency. I was running 60 hertz. And this last function I'm showing here is crest factor. Now, crest factor is a ratio. You'll see no units. It's a ratio of the peak value to the RMS value. And this has a lot to do with some of the components you may have in your circuit, some maybe digital devices, A to Ds, whatever it may be, where you're looking at that peak to RMS value. Also has a function to do with the distortion of the waveform. If you had high peaks, crest factor could be a lot different. So, on a sine wave, the peak to the RMS is basically the square root of 2, and that's about what we have here. So this is a voltage waveform. The green is the current waveform, and they were both sine waves from the source that we used. Now, when we're making our power measurements, our input to the power meters, the power analyzers, are somewhat limited, regardless of which brand that you're using. So we do have to typically step down the current in your overall measurement of your system. We offer a lot of different types of current transformers. We have clamp irons that we resell as a distributor from AEMC, nice clamp irons. They're probably in a 0.3 to 0.5% accuracy class and several different current ranges. Scope probes, we'll talk about those in a minute. Nice small scope probes, good for scopes. Yokogawa does manufacture a few of our own precision current transformers and voltage transformers where we can feed the cable through the window or make actual connections up here at the top on these terminals where we break the line. For DC measurements, again, we work with, as a distributor, resell RAM-meter shunts. So we put these in line to measure DC. They are for DC. Another popular current transformer is from Pearson Electronics. These are very high frequency coils, and if you're getting into real high frequency components and waveforms, used an awful lot in the lighting industries, electronic ballast, and things like that. So from Pearson Electronics. Then we also have another system, which is a precision measurement current transformer. It's a whole different type of technology they call the zero flux technology current transformer, and a system that we developed together with Dan Physics, which is now part of LEM, and this provides some real interesting applications from DC up into the hundreds of kilohertz area. Very high accuracy from like 0.05, 0.02% of the full scale. So we have a lot of current transformers that we can help you with your application. Selection considerations for a current transformer. Accuracy on a CT is typically what you would see as the CT turns ratio when you're looking at that. Another important part that you need to consider is the phase shift. We're measuring power, and phase shift is will affect the power measurement. How much phase shift depends on your application. Say if we had a 1 or 2 degree phase shift, the cosine of 2 degrees is 0.9994. Is that acceptable in your application? Some, it's not a problem. Others, like in high accuracy measurements, transformer testing and things like that, that's not acceptable. Then you need to consider the frequency range. For DC measurements to about line frequency and a little bit higher, if they're sine waves, we can use DC shunts. But they're not acceptable for high frequency and highly distorted waveforms. They don't work on that. If we're using DC and AC type of waveforms, there are current transformers that have a Hall effect sensor in them. The Hall effect lets us sense the DC. However, with that technology, we do lose some of the accuracy in a 2-3% area maybe. Or the active type, like the Lambda and Physic CTs that we have now, with the electronic active type circuit in the CT, 0.05, 0.02%. Normal instrument type current transformers like the ones we make, or utility transformers, typically those are good for about 30 hertz and higher, and there's a lot of different types of these CTs available. And again, we can help you with that in your application. Now, the other thing you have to think about is compatibility. What's the output of that current transformer? A typical instrument transformer has a 5 amp output. Some of these other clamp irons may have a milliamp or millivolt per amp output. You have to consider the impedance or the load that the CT is going to be connected to. How much lead length you have, how many instruments might be in the circuit. So we do have to figure that. There'll be a burden. Scope probes, I say caution, use on scopes, not on the power analyzers. The power analyzer has a different type of input circuit than a scope typically does, and a lot of times we will see problems because they are not matched with the electrical input characteristics of the amplifiers of the two different types of instruments. Then, of course, your physical size, how much room do you have, to make put your CT in the circuit. Clamp irons, they're very handy. If you don't have to break the wire, just clamp it on the conductor. You do lose a little bit of the accuracy with clamp irons, or the donut type, which is a through type, transformer, better accuracy, but you do have to break the line someplace to get it over the cable. And then the distance, from the load or your CT, back to the instrument, you have to consider those physical characteristics also. Now here's a word of caution. Never open circuit the secondary side of a current transformer while it's energized. This can cause damage, serious damage, to the CT, and even could cause possible harmful damage to the equipment or the equipment operators. Here's what happens. A current transformer is a current source. So just going back to Ohm's law, voltage equals I times R. What happens when R becomes very large? E, the voltage goes very high, and this internal voltage within the current transformer will just self-destruct the CT. So that very high voltage generated inside the CT can cause a magnetic saturation of the core, can cause actual winding damage or some other damage that can destroy the CT. So always never open circuit the secondary side of a current transformer while it's energized. Be careful. Okay, let's look at the what we call a single-phase 3-wire measurement. So we got a load. We have line 1, line 2 coming out of it. We have a neutral. This is like the power lines we might have in our North American residential service for electric ranges, electric dryers, where we have we call this a split phase or a single phase 3-wire type measurement. We have two lines that are providing the current and a neutral. So since we have two lines that can provide current, we've got to measure each line because we don't know what's inside this box. They can have different loads between line and neutral. So we're going to put a wattmeter on both lines, measure the series current, measure voltage line to neutral. It's a 2-wattmeter method. Total power is going to be the sum of the wattmeter reading number 1 and wattmeter reading number 2. Now these could be two analog meters, simple analog wattmeters. It could be a more sophisticated power analyzer that has multiple inputs. But the total power is going to be the sum of the two readings. Now, in the single-phase 3-wire system, which we call split phase sometimes, voltage current detected by the meters are the actual voltage current applied directly to the load. The indication on each meter is the power that's being delivered by that line to which the meter is connected. And then the total power is just the algebraic sum of the two indications. Here's a display from one of our power analyzers. So I had line to neutral 111.86, 111.44. My two powers 2.326 and 2.4. These two will total up to the total power, which is what I'm showing here is my total power. Now I've circled these two currents, and here's what I want you to look at. Here's a current of 20.7. Here's one that's a lot higher, 22.6. That's why we have to measure the current and the power in each line, because we don't know what's inside and what's being drawn, by that device. My line to line voltage was a 223, and my total VA 4.8. We can look at the VA on each side. Now, here's something interesting. If we look at one of the power factors, it was unity, total resistive load. We look at the other power factor is 0.99, so there's something in there on half of the circuit that's different. Some other probably inductive device. Here's the waveforms on this. This is the line-to-line voltage. This is one of the line-to-neutral voltages and the other line-to-neutral voltages. You'll see the way the meter's hooked up, the way the meter sees them, they're 180 degrees apart. This is one of the currents, and this is the other current. Now, this negative current, see, it's 180 degrees out of phase, so this negative current and that negative voltage will give us a positive power. Actually, what this device was an electric dryer. So part of the circuit was a resistive heating load. The other part of the circuit had resistive heating load as well as the motor, which was part of the inductive load, which caused us that lower power factor. So that's why you have to monitor on a split-phase system both lines unless you know exactly what's inside that device. We can also show you a phasor diagram, and this is on the same split-phase single-phase 3-wire system. Here's the voltage and the current on one side where we had total resistive load. They're in series or in phase with each other. And here's our voltage, and we did have a little phase shift due to that inductive load from the motor on the other side. Now, Blondell's transformation, Blondell's theory, states that total power is measured with one less wattmeter than the number of wires. So let's go back and see what we've done. On a single-phase 2-wire system, very simple, we used 1 wattmeter. On our single-phase 3-wire system that we just did, we used 2 wattmeters. Now as we move into a 3-phase 3-wire system, there's 3 wires, we're going to use 2 wattmeters. And on a 4-wire system, we're going to use 3 wattmeters. So just because it's a 3-phase 3-wire, some people think they're going to have to use 3 wattmeters. To measure power, we only need 2. Now putting all 3 circuits in there can be an advantage on some of the other measurements we're going to show you later. So if we think about our 3-phase system as generated from the power utility, the voltages, they're all balanced, real nice, 120 degrees apart in phase. And if we look at them with a waveform analyzer and we look at the line to neutral phase relation, and 120 degrees apart. And here, again, if we look at them, measured line to neutral, we got our sine waves, and everything is balanced, 120 degrees apart, measured line to neutral. So now, we're going to look at a 3-phase measurement. We're going to start with a 3-phase 4-wire system. We got a load, we got 4 wires coming out of it, and we got our 3 phases for the power, and then we have the neutral. Typical distribution voltages here in the U.S., North America, line to neutral voltages that we see on something like this, distribution voltages, 120 or 277, measured line to neutral. If we measure those line to line, they're going to be a little bit higher. The 120 is going to be the 208, and the 277 is going to be the 480. The relation there is the voltage, the line-to-line voltage, is going to be the square root of 3 times the line to neutral voltage. So the line-to-line voltage is going to be higher, right? That's what we see here. So on our 4-wire system, we're going to put 3 wattmeters. We're going to put that in each of the 3 phases that are supplying the current. And remember, we're going to watch the polarities. We're going to measure the current in series and the voltage line to neutral on each of the wattmeters. Current in series, line to neutral voltage on each one of them. And the voltage and the current, again, we have to follow the instructions on the instrument, on the unit, exactly how to hook it up with the correct polarity, because that's the way the engineers designed it, so that we get everything the right phase, we make the total calculations, and get the correct value. Now, on a 4-wire system, the total power is just going to be the sum of the 3 wattmeter readings. So these could be individual wattmeters. It could be a special 3-phase type of a power analyzer that's going to sum everything for you. But it's just the total of the 3 readings. So the 3 meters use the 4th wire as the common voltage reference. Each meter will indicate the true phase power. And the total power is just the algebraic sum of the 3 meters. And so basically this is like 3 single-phase measurements. So if we look at our power analyzer on a 3-phase 4-wire system, and we got the 3 power readings, the 22 is pretty well balanced, get our 66 as our total. And we can look at the other phase parameters such as phase power factor, each of the phase currents, and these were the voltages, phase voltages. And my frequency on this device was a little bit lower, is 30 hertz. So if we again look at the waveforms, we can see with the power analyzers, the actual phase voltages and phase currents and their relation to each other. Remember, the voltages are measured line to neutral. Then we can see our vector diagram of the voltages are right on the 120-degree line. These are our phase-shifted currents. Then we can get the current shift up 39 degrees on each one. See the balance in a picture of a vector diagram. Now, let's look at a three-phase, three-wire system. So we got a box, we got 3 wires only coming out of it. The only thing we can measure are the series currents and the line-to-line voltages. Now, power in a balanced three-phase, three-wire system, you can estimate that before you get started. And so the total power is going to be the square root of 3 times the line-to-line voltage times the phase current times the power factor. So you're going to have some idea of what that power factor of your device is. If it's a motor fully loaded, you might try to put in a power factor of 0.8. But the line-to-line voltage, you could measure one of them. You could measure all 3 of them and average them, the same with the current. But you're going to get a value for the line-to-line voltage and the phase current multiplied by the square root of 3 because it's a line-to-line measurement. That will give you an approximate idea of what that total power is. And that'll work if your device internally is wired as a delta or a Y, because we're still making a line-to-line voltage measurement. So on our 3-wire system, 3-phase, 3-wire, if we put a wattmeter on each side, measure all 3, we can do that and look at your phase currents on each one and the line-to-line voltage. So in the 3-phase, 3-wire system, the wattmeters in this connection, they measure the phase currents, okay, because the currents are in series. But the voltages are not phase voltage, they're line to line. Therefore, the indication on the meters is not a phase power measurement. And I call this kind of a very non-intuitive connection and non-intuitive calculation, and people get confused as to what they're getting. What's happening, we think if we look at the red vectors, that's our line to neutral measurement, and those are 120 degrees apart, as generated by our power utilities. And I've drawn in some arbitrary current vectors at some phase shift. But now the meter is not connected line to neutral. The meter is actually connected line to line. So the way the meter is connected is in a delta, okay, configuration. So all 3 voltages in here, the way the meter sees the connection is in a delta. And these voltages on a balanced system are 60 degrees apart, not 120. And then if this current comes back up in phase, to say the red line here, you'll see that the current is actually has an additional 30-degree phase shift between that current and that voltage. So the power analyzer has to take all this into consideration when it's making these measurements. And the main thing is that you're not making a phase measurement. It's not a phase voltage. The voltages are in a delta configuration. So all of our power measurements that we've talked about so far have had one thing in common, that the meters used to determine total power had a common connection between them. In the 4-wire system, the common point was the neutral. The voltage was measured line to neutral. Okay, in the 3-phase, 3-wire system, the common point is one of the phase connections. So on a 3-wire system, we only need 2 meters to measure total power. Remember Blondell's transformation. Total power is measured with one less wattmeter than the number of wires. So we go back to our 3-wire system. We don't need this third one. We need 2 wattmeters to measure total power. Measure a current and a voltage from a line to line, and in this example, the B phase has become our pseudo-common, where we measure C to B and A to B in each of the phase currents. Now we can put the wattmeters in here, and we look at the power on each one. We got power 1 is 22, about 22.5 and 8.3. They total up to the 30. If we put the third one in there, we don't use it to get total power. We can look at all 3 voltages and all 3 currents, but the total power is the sum of just 2 wattmeters. And you'll see this is not phase power because these are not equal, they're unbalanced, and that's just because the way the wattmeter is set up and the phase reference that it sees between the 2 of them. The 2 wattmeter method tends to cause, I say, less confusion because you're not expecting to see the phase power. We do one thing in our power analyzers, and then on a 3-phase 3-wire system, we have a configuration we call the 3V, 3A, 3 voltage, 3 current wiring method. And this method will give all 3 voltages and all 3 currents. It'll give a correct total power factor, and VA measurement on either balanced or unbalanced 3-wire system. So we can see all 3 voltages and all 3 currents, and if it is unbalanced, we will make correct measurements with that. So if we look at our system, here's a 4-wire system. If we measure a 4-wire system just using 2 wattmeters in the 3-phase 3-wire method, that power is going to be the same whether we measure it as 3-phase 3-wire or 3-phase 4-wire. You get a device out here that's drawing the same power. So regardless of how you hook it up and measure it, you're going to get the same power. Here's an example from our display, hooked up to a common load 3-phase 3-wire connection, and our power here was 40.87, and on the 3-phase 4-wire connection on the same device simultaneously, they had 40.89, basically the same power factor. Now you'll see the voltages. This is your line to neutral voltage, 55.2, and this is a line to line, 95.6, and it calculates out exactly correct. The phase currents, either method, are the same. And if we look at the waveforms, this is the 3-phase 3-wire connection. You'll see the waveforms 60 degrees apart. And the currents are phase currents, so those are 120 apart. Here's the 4-wire system. The meter sees those 120 degrees apart, as well as the phase currents 120 degrees apart. Let's look at some applications. One of them that we get into quite a bit with all the energy things that are going on, standby power, Energy Star measurements, and a new thing that's come up along these lines is the IEC 62301 testing, which kind of goes along with Energy Star and standby power. I'm going to cover these a little bit for you. Just briefly here, the IEC 62301 is becoming an international standard, and it really applies to household electrical appliances and the measurement of standby power. And this is a hardware-software measurement solution. So this is an international standard. If you're dealing in any type of household appliance, this may come up. So standby mode is the lowest power consumption mode that cannot be switched off, by the user, and it may persist, for an indefinite time when the appliance is connected. And think about standby power. Just think about things in our home, like the TVs with the remote control or any device like that. They're always in a standby mode, waiting until you turn that main power switch on. So it's interesting if you look around your house just to see how many things, power bricks and things like that they have that are always plugged in and always running. And so standby power is average power in a standby mode when measured in accordance with the standard. Here's some examples of these different types of standby modes. They may have some type of measurement device in here. There's 7 different types that the standard defines for the sleep mode. Now, standby power, here's what I like to show you is a pulse mode of power. And think about something like a laser printer or copy machine. It's got heaters in it that are always cycling off and on. And we get these instantaneous, power bursts when the heaters turn on, then they turn off, and we get another boost of power. And so things are always, turning off and on, and we have to average this over time. And so, when we look at this, we're going to average out that power reading. And then several different power consumption methods that they talk about in the standard that that we use, and this is all defined in the standard. And if you're doing this type of work, have questions, we can help you in that area. So the energy consumption is specified over some period of time. So our standby power measurement, we use what's defined as the third method, that energy divided by time. And so we run the integrator in the power analyzer and get watt hours, and then we divide out the time to get an average power measurement. And our power analyzers measure the true average power over a user-selected time period. And this is what we call average active power, which is defined in this standard. And it's the preferred method as it works on both steady state and fluctuating power sources. So average active power is what we use in that. And this was pioneered by Yokogawa back in the year 2000 with one of our earlier power analyzers, the WT200 series. And then section 4.5 defines the power accuracy and the resolution that is required to make these measurements. One of the important things is that the measuring instrument must have a minimum current range of 10 milliamps, and this is to do the standby power measurement. Some typical systems that we could provide, with our power analyzer, we have an outlet cord for 120 volt, 15 amps that you can just plug your load into, and the IEC 62301 software is a free download from our website. Now, this standard refers to 25 different household electrical appliances, so it really breaks it down into, each one. And it pretty well follows the Energy Star standard from U.S. and North America. And I'm not going through each one of these, but you can see, all the additional standards and how each one of these has its own set of test measurement criteria. Some, any type of household appliance. Let's look at some other applications. Here's one that comes up is what I refer to as reflective power measurement. That's the power that's kicked back on the line from one of our devices. So the way we do this is we look at use the integrator, where we can look at the net energy, and we can break this energy flow down to the forward and reverse energy. And so here's the forward energy, and then this is the energy that's kicked back. It's energy, it's watt hours. Here's our true power. I ran the integrator for 10 minutes just as in this example. And then what we do is we calculate, we break out just the time value, come up with what we call the reflective power. This is power being kicked back out on the line. And this was, in this case, is reverse flow, 361 milli reflective watts is what I called that, okay? So it's power. And the way we do this is an average active power measurement, which we talked about earlier. And we measure the watt hours, which is our reverse energy, and then we multiply that by 3,600, and then we divide by the time in seconds. So I had 10 minutes, converted that to seconds. And that's how we get this number. So a lot of times in your power quality work and your design work, you want to know what's being kicked back out on the line. Here's a motor drive application. If you're involved with motor work, we have a full seminar on motor drives, but a pulse width modulated PWM voltage signal where we vary the frequency of the voltage, which varies the frequency, speed of the motor. Very hard measurement to do in looking at these types of waveforms. We've got a lot of switching noise on the currents, but we can look at the total power, total VA. The motor in this case was running about 28 hertz, but we can measure all these methods. We can look at the DC bus voltage on that PWM, typically as a peak value. And on this PWM voltage, this is where we usually make one of those mean measurements because that mean algorithm would give us the fundamental voltage that we're looking for. But we cover this in another extensive seminar. Now, drive efficiency, of course, you know, that's calculated as output power divided by the input power, and usually as a percentage. And so to do this on a variable speed drive, you could use two power meters to measure input power and output power. One of the problems there is a time skew between the two readings. And what we recommend is using a multi-element power analyzer so we can make those measurements simultaneously, and then we can calculate the efficiency you know, in the single power analyzer, and that's going to eliminate any of the error due to the time skew. Here's a menu setup in one of our power analyzers where we're looking at the drive efficiency. This is the output power. In this case, it was a three-phase. We had a single-phase input, so we just put that formula right in the you know, the power analyzer, and it's going to calculate everything for us and give us the efficiency measurement. So here's an example of our drive efficiency. This was the input power, about 55 watts. The output power, almost 31 watts. And our efficiency is calculated, in this case, at about 56%. We can also look at the watt loss, the power loss within that device. And efficiency is pretty low because the motor is not loaded. It's running at a very low speed in this example. But those are things you can do in the power analyzers and, you know, with your measurements on efficiency. Now, this was shown on a drive. The efficiency could be done on a similar type of a unit under test. Startup analysis, you know, what happens when we start up a device? We turn it on. Here's an example of a device. The voltage is always on. We turn the power switch off or on, and current starts flowing. Boom, we get a spike here, and we can see what happens with our unit starting up. And we can look at a cycle-by-cycle startup power measurement. The power's off. Within one cycle on this, or within the second cycle, this device had started and was running at its constant power. It may take other devices several cycles to start up, and all this you can see with different you know, power analyzers on how to analyze that startup condition. Cover a little bit on a power digital storage oscilloscope. The power analysis done with the math capabilities. It does have dedicated probes, ease of connections. With a scope, we can have very high bandwidth, and some of our scopes we can have 4 to 8 channels. We can do harmonic analysis to IEC standards, and with a scope, the thing we have to do, and we'll show you here in a minute, is the probe phase compensation between the two channels. So here is what we're talking about is a Deskew calibration. In other words, to get a true power measurement, we're not multiplying just one channel times another. There can be phase differences between those two probes. You got one voltage probe, you got one current probe, different signal path, cable lengths, everything that could cause a signal delay, time delay between the two. So with our power scopes, we have a Deskew box, hook up the voltage, hook up the current. This has the little power from the power supply. we minimize that deskew time. Typical measurements we might do with a scope are board level power measurements. This is probably the best application when we're doing board level work. Switching device, switching component power losses, device power consumption, noise levels. We can do the harmonics, look at output power and stability over time. So when we get down to a component level, here's a switching device where we can look at the voltage and the current on the switching device, and from the waveform math we can calculate the losses during turn on, steady state operation, real easily, component level with the scope and the probes. Okay, part two, let's look at some power factor measurements. In an AC circuit, we typically have components of inductors, capacitors, and resistors. These could be in some series parallel combination, but we usually have those three components within a circuit. With an inductor, the current will lag the voltage in time going through an inductor. All right, in this example, I got my two sine waves. The voltage is the yellow, the green is the current. This would indicate or represent an inductor where the current is lagging the voltage in time. And so I had 120 volts and 1 amp. Had a power factor of 0.7. And here I look at the phase angle. We'll use G because it is lagging. Lead and lag both start with L, so we use the last letter. So we're looking at G as a lagging. And so if we got 44.77 degrees, we take the cosine of that angle, 0.70994. That's basically our power factor. In a capacitor, the current is going to lead the voltage. Now here my green waveform is the current. In time, it's leading the voltage. Similar type setup, I'm using D to indicate that it's a leading phase angle. The phase angle was 45.09 degrees. Cosine of that is 0.70599, basically what the power meter read. Some real-world examples, say an inductive load with an AC motor, the current's going to lag the voltage because it's an inductor. Here's a capacitive load because of the ballast in this particular compact fluorescent lamp, where the current is leading the voltage, the capacitor. So if we look at a waveform, this is off a power supply. Got our voltage, got our current that turns on at the peak of the voltage, and how do we accurately measure the phase angle between these two waveforms? Well, to do that, you've got to know where your zero crossing reference is. Everybody here would tell me something different as to the phase crossing reference. For a sine wave, power factor can be calculated as a cosine of the angle between voltage and current. It's a sine wave only. This is defined as displacement power factor. Okay, it's the displacement in time or degrees from voltage to current. But for all other waveforms, these distorted waveforms, power factor is calculated as watts divided by VA. This is defined as true power factor. Works on any type of a waveform. Going back to our power triangle, we have watts on the base. By convention, inductive load, VAR is drawn upwards, and then the volt amps. And then we calculate this power factor as from our trig calculation of watts divided by VA as the angle between here. So true power factor measurement in this example on our power supply, watts divided by VA, I got 0.76651 as our power factor. We measured our watts, we measured the VA, and we calculated the power factor. Now here's an example of a displacement power factor. If we look at our vectors, and we had a displacement of 21 degrees, 21.06. We can see up here that our power factor, lambda, was 0.933. And if we do that calculation of watts divided by VA, we get 48 divided by 51.933. Okay? So it works both ways. Exactly the same measurement. This is on a sine wave. Now, power factor on a three-phase system and a three-phase four-wire system, total power factor is total watts divided by total VA. Well, we know the total watts is just the sum of the 3 wattmeter readings, and the total VA is the same, the sum of the 3 VA measurements. On a three-phase three-wire system, our total wattage is the sum of 2 wattmeters. Total VA is it's the square root of 3 because it's a line-to-line measurement. We look at VA1 and VA2, and we divide by 2 to get the average. Now, if the load is unbalanced, say the phase currents are different, this could result in an error in calculating the power factor since only 2 of the VA measurements are made. Okay. So if one of these VAs was higher, you can see this math calculation is not going to be right. So with the 3 wattmeter method, which we call the 3V3A wiring method in our power analyzers, is total watts divided by total VA. Total watts is still a 2 wattmeter method. Now we look at all 3 of the VAs, multiply by the square root of 3, and then we divide by 3 to get the average. Now this works on either a balanced or an unbalanced 3-wire system. That's one of the advantages of using our 3-voltage, 3-current wiring method. So looking at the 3V3A measurement method, our total power is power 1 plus power 2. So that's our 49 watts here. And then we look at the, this is a 3-wire system, so we cannot look at phase parameters. We look at the 3 VAs, okay. Got our total VA, total watts divided by total VA. Okay, watts divided by VA is going to give us our total power factor in this example of 0.5. So 49 divided by the 93, that's about half, right? So that's going to kind of bring us to a conclusion with our 1-hour seminar here. We tried to cover a lot for you, cover quick, but hopefully this is going to help you understand, basic power measurements in our single-phase and 3-phase circuits. What we're talking about with a 2 wattmeter and 3 wattmeter method, some sample applications on single and 3-phase measurements, a little bit on using a digital oscilloscope for the power measurements. And then when we looked at power factor, hopefully we didn't confuse you too much on that. We talked about displacement power factor, so if you're dealing with true sine waves, like in our power utilities, we can look at the displacement as cosine of theta. But for all of our power electronics applications that we're doing today, we got to look at a true power factor. And we gave you some examples of some power factor measurements in a single and 3-phase circuit. And hopefully we've answered your questions. If you do have other questions, feel free to submit them, because we've just about filled up our hour, and we don't want to hold you too long. So with that, I thank you for attending.